Signal flow graph reduction. Signal flow graph of a control system can be reduced either by directly applying the rules of signal flow graph or by using Mason's gain formula. Here we are going to see how to apply Mason's gain formula to find the overall gain of the system or the transfer function of the system. According to Mason's gain formula, the overall transfer function of the system T of S is equal to 1 by delta K summation over K P suffix K delta K. T of S is equal to transfer function of the system K is the number of forward paths present in the signal flow graph. P suffix K is the forward path gain of the kth forward path. Delta is equal to 1 minus sum of individual loop gains plus sum of gain products of all possible combinations of two non-touching loops minus sum of gain products of all possible combinations of three non-touching loops plus sum of gain products of all possible combinations of four non-touching loops and so on. Delta suffix K is same as delta, but for the part of the graph which is not touching the kth forward path, that is we have to exclude all the branches which touches the kth forward path, and then if we calculate this value of delta, that we call it as delta suffix K. So by applying this Mason's gain formula, T of S equal to 1 by delta into summation over K P suffix K delta K, we can find the overall transfer function of the system, or we can find the overall gain of the system, where K represents the number of forward paths present in the signal flow graph. Now let us consider this signal flow graph. Our aim is to find the overall transfer function of the system. Here we are going to apply Mason's gain formula to find the overall transfer function of the system. Here in this given signal flow graph, the input is R of S and output is C of S. Our aim is to find out the overall transfer function C of S divided by R of S. Here we are going to apply Mason's gain formula. In this signal flow graph, totally we have 8 nodes, 1, 2, 3, 4 up to 8. Between 1 and 2 we have a branch with gain 1. Similarly, for between 2 and 3 we have a branch with gain G1, here G2 and G3, G4, G5, and at the output node we have a branch with gain 1. Here we have a forward path with gain G6. Here between node 3 and node 5 we have a negative feedback path minus H2, and between 3 and 4 also we have a negative feedback path with gain minus H1. According to Mason's gain formula, T of S is equal to 1 by delta into summation over K P suffix K delta K. So here in this formula we should find the value delta K, P suffix K and delta K. Then if we substitute it here, we will be getting the overall transfer function T of K. So here in this summation we need to find the value of K. K is the total number of forward paths in the signal flow graph. So first let us start with finding the total number of forward paths. So if we consider this signal flow graph, here we have forward paths which starts from input node and output node. If we traverse across 1, 2, 3, 4, 5, 6, 7 and 8, this forms one forward path. Similarly, if you traverse through 1, 2 and then 5, 6, 7 and 8, this forms second forward path. So totally in this signal flow graph we have two forward paths. We have two forward paths, so we can assign k is equal to 2. Now let us draw the two forward paths. First forward path, so this is the first forward path which starts from the input node R of S and ends at C of S. So if you find the forward path gain of this forward path, that we can represent it as P1. P1 represent the gain of the first forward path. So if you multiply all these gains, that is 1 into G1 into G2 into G3 into G4 into G5 into 1. So we will be getting G1, G2, G3, G4, G5. So this is the forward path gain of the first forward path. So we represent it as P1. Now let us consider the second forward path. The second forward path starts from input node 1 and then 2, then directly to 5, then 6, then 7, then 8. So this is input node R of S and this is output node C of S. This path forms the second forward path. So if you want to find the gain of the second forward path, we can write it as P2 is equal to 1 into G6 into G4 into G5 into 1. So P2 is equal to G6, G4, G5. So this is the gain of the second forward path. So according to Mason's gain formula, we have to apply this T of S equal to 1 by delta summation over k P suffix k delta k. We found the value of k. Here in this given problem, the value of k is equal to 2. So we can expand this formula. T of S equal to 1 by delta into summation over k is equal to, since the value of k is equal to 2, we substituted the limits k is equal to 1 to 2. So if we expand this expression, we will be getting 1 is equal to 1 by delta into p suffix 1 delta 1 plus p2 into delta 2. P1 is the forward path gain of the first forward path and P2 is the forward path gain of the second forward path. So we found these two values P1 and P2. So now we have to find out this delta, delta 1 and delta 2. If you know these values, we can directly substitute it and then we will be getting the overall transfer function T of S. Now based on this formula, we have to find out the value of delta. So the formula for delta is equal to 1 minus sum of individual loop gains plus sum of gain products of all possible combinations of two non-touching loops and so on. So our aim is to find out sum of individual loop gains. So we have to identify the individual loops in the signal flow graph. So if you consider this signal flow graph, here if we take this node 3 and 4, we have a loop that starts from 3 and goes to 4 and then again come back to 3. So this forms one loop. Again if we take 3, 4 and 5, here from 3 to 4 and 4 to 5 and again come back to 3. So this forms another one loop. Similarly, if we take 6 and 7, here also we have feedback paths. So it starts from 6 and go through this G5 and then come back to this 6 through minus G3. So this forms the third loop. So our aim is to find sum of individual loop gains. So let us draw the individual loops. So here we have three loops. This forms the first loop and this forms the second loop and this forms the third loop. So we can find the individual sum of loop gains. So the gain of this first loop we can write it as P11, which is equal to G2 into minus H1. So we can write it as G2 H1 minus G2 H1. So for the second loop we write it as P suffix 21. These 2 represent the second loop and this 1 represent the individual loop gain. If we go for 2 non-touching loop, the second suffix becomes 2. So here the loop gain is equal to G2 into G3 into minus H2. So we can write it as minus G2 G3 H2. Similarly for the third loop we can write it as P3 because it is individual loop gain, so 1. For 2 non-touching loops we use the second suffix as 2. So here P31 is equal to G5 into minus H3. So we can write it as minus G5 H3. So we got the 3 loop gains P11, P21 and P31. Now based on the formula we have to find out the sum of gain products of all possible combinations of 2 non-touching loops. So if we consider this signal flow graph, we have taken this as one loop and this is another one loop and this is third loop. If we take this loop and this loop, that forms one non-touching loop, and this loop and this loop forms another one non-touching loop. So now we are going to draw the 2 non-touching loops. Gain products of 2 non-touching loops. So first we are going to take this loop and this loop as one combination of non-touching loops and this loop and this loop as another combination of 2 non-touching loops. So first let us consider this loop. So we have taken 2 loops. First one is this loop and second one is this loop. So 2 are non-touching loops. So 2 non-touching loops we have taken. So the next combination will be this loop and this loop. Both are non-touching loops. But if you take these 2 loops, here we have 2 common points. So we cannot take these 2 loops as non-touching loops. So now let us take this loop and this loop. So for these 2 non-touching loops we can write the gain formula as P12. this 1 represent the first two non-touching loops and 2 represent the two non-touching loops. So P12 is equal to, for this loop the gain is minus H2 into G2 into G3. So we have written it like this. Then for the second loop the gain is minus H3 into G5. So minus H3 into G5. So this can be expanded as P12 is equal to G2, G3, G5, H2, H3. So for the second two non-touching loops, the gain can be written as P2 because it's a second non-touching loop, because it is two non-touching loops, so P22, which is equal to this gain of the first loop minus H1 into G2 into G5 into minus H3. So we can write it as minus G3 into H3 into G5. So the product will be G2, G5, H1 and H3. So we found the value of P12 and P22. Next our aim is to find the value of delta. So from this formula, delta is equal to 1 minus sum of individual loop gains plus sum of gain products of all possible combinations of two non-touching loops. So we found this one and we found this one. The third component is sum of gain products of all possible combinations of three non-touching loops. So from the given signal flow graph, we have three loops, but three loops are not non-touching. So we cannot take three non-touching loops from this given signal flow graph. So we can leave the third component. So to calculate the value of delta, we need the sum of individual loop gains and sum of gain products of two non-touching loops. We don't need the third value. Next we have to calculate the value of delta. So based on this formula, delta is equal to 1 minus sum of all possible combination of these individual loop gains and then two non-touching loops. So for individual loop gains, we already derived those values. So P11, P21 and P31. So P11 plus P21 plus P31, then plus two non-touching loops. Here we have P12 and P22. So P12 plus P22. Now we have to substitute the values of P11 to P31 and P12 to P22. So this is the value of delta. So now our aim is to calculate the value of delta 1 and delta 2. We found the value of delta P1, P2. So now we need to find the value delta 1 and delta 2. So as per the definition, delta 1 means we have to exclude the first forward path from the signal flow graph, and then we have to find the value of delta. So here in the signal flow graph, if we exclude the first forward path, that is this path, if we exclude this path, then we cannot find any loops by excluding this forward path. So the value of delta 1 is equal to 1, because the formula is 1 minus sum of individual loop gains. So we don't have any individual loop after excluding the first forward path. So we can consider this delta 1 is equal to 1. Then to calculate the value delta 2, we have to exclude the second forward path. If we exclude this second forward path from here, we will be getting only one loop, that is this loop 3 to 4. So we will be getting only one loop we are getting. So we can write the formula as 1 minus P11, so which is equal to 1 minus the loop gain is H1 into G2, so minus H1 into G2. Here we don't have two non-touching loops because we have only one loop, so the value of delta 2 is equal to 1 plus H1 into G2. So now we know all the values, delta 1, delta 2, P1 and P2. So now we can substitute all these values in T of S, so we can find the overall transfer function. The formula is T of S is equal to 1 by delta into P1 delta 1 plus P2 delta 2, then P3 delta 3 value is 0, so this value we have to substitute. So we know all the values, so we can substitute it here. So 1 by delta, then into P1 into delta 1. Into the value of delta 1 is equal to 1. Then plus P2. P2 is equal to G6, G4, G5 into the value of delta 2 is equal to 1 plus H1 G2. So if we multiply this value inside, we will be getting the overall transfer function of the system. So for this signal flow graph, this is the overall transfer function of the given system. So by applying Mason's gain formula, we can find the overall gain of the any given signal flow graph.